Let us start single slit diffraction. We all know that diffraction is a phenomena in which wave will encounter any kind of obstacle or opening. So let us see what will happen to diffraction if the wave is passed through a single slit, right? So here you can see a pictorial diagram of this particular experiment. So there are two lenses, as you can see here. Lens 1 is placed near to the source and lens 2 is placed near to the screen. In between both the lens there is one slit, that is a disc with one opening, right? So this opening is nothing but our slit. This opening A to B is our opening and it is termed as slit. So now here you can see this is our source, this is our lens number 1, lens number 2. This is our slit, and last one over here is our screen, which will collect the results or which will collect the outcome of this experiment, right? So now as you can see here, source will give waves or light. That light will pass through lens number 1 and the plane wave front, as you can see here, will move towards the slit. Once it will move towards the slit or it crosses the opening of slit, as you can see, there will be some deviation of angle which is theta, and by that particular angle this wave front will be directed to lens 2. Moving from lens 2, it will then converge at one particular point, and that is the point over here on the screen. So light is incident at a given point in the space downstream of the slit is made up of contributions from each of these sources, and if relative phase of these contributions vary by 2 pi, we can get or we can expect to find minima and maxima in this particular diffraction of light, right? Such phase differences are caused by difference in the path of length over distributing rays which are reaching towards our slit, right? Or which are rays which are reaching the point from the slit. The analysis of this system can be more simplified if we consider single wavelength of the light, or if we consider light is having the same wavelength, then if the incident light is coherent, these sources all of have the same phase, right? So this is a single slit diffraction experiment, and it is very much important for us to understand the phenomena of diffraction or how a light reacts when it is passed through a small opening. Moving ahead to defects of optical images. So let us see why these defects are occurring, right? Defects of optical images are generating or occurring due to 3 reasons. These are the main 3 reasons which are responsible for defects in optical images. First one is parasitic light. So what do we understand by parasitic light? It is produced by internal reflection at the surface of lens and by scattering of light by dust particle or small defects in the glass, such as bubbles which may form inside the glass, right? And this phenomena is also known as Willing glare. Please remember that parasitic light defect is also known as Willing glare. So this Willing glare is basically produced due to internal reflection of surface of lens, and by scattering that light out of dust particle or some small defects. It is greatly reduced by applying anti-reflecting coating on glass and by hermetically sealing portions of an instrument, right? So to overcome parasitic light, what we can do is we can apply some anti-reflecting coating on our glasses, or we can go for hermetically sealing our instrument lenses, right? So this is our first defect. Second defect is aberration. So what do we mean by the word aberrations? The image formed by a lens can be distorted by aberration, both chromatic or spherical, right? To eliminate this error, suitable shaping of lens or introducing correcting element is much needed. So make sure that whenever you are having issues due to aberration, you must go for either shaping of lens or you can introduce correcting elements. Clear? Then coming to diffraction, in focusing an image, a lens passes only the light that falls within the circular perimeter. From this point of view, a lens behaves as a circular aperture in an opaque screen. A lens behaves as a lens will behave as a circular aperture in an opaque screen. Such an aperture forms a diffraction pattern which is analogous to that of a single or double slit. Thus, diffraction effect often limits the ability for telescope, microscope or other such instruments to give us a precise image. Limit of resolution. This is one of the most important defects occurring in optical images. It is due to limit of resolution. As the name itself suggests, there is some error in resolution of images. No optical system will transmit the whole wave which is emitted by the object, and there is always some diffraction. Due to this, when aperture is circular, the image of a point source consists of airy disk and surrounding ring pattern. This will limit the resolution of image, resulting in poor image resolution, right? So when the aperture is circular, the image of a point source consists of airy disk and the surrounding ring, as you can see in this particular picture. When angular separation of 2 point sources is sufficiently great, when angular separation between 2 point sources is very much large, the diffraction pattern which forms the image do not effectively overlap. Such images are said to be resolved, right? In that cases, images are said to be resolved when there is a sufficient distance, right? Or when they are separated with a quite huge distance. But when angular separation between 2 point sources is very much less, then angular radius of this particular airy disk, the two images is then superimposed to an extent that they cannot clearly distinguish between the two images, but due to one object alone, right? Such images are termed as unresolved, right? So there is 2 points to remember from this limit of resolution: what is resolved image and what is unresolved image. In case of resolved image, angular separation between 2 points is sufficiently high, whereas in case of angular separation between two sources, when it is very much less, the image so formed is unresolved. Now let us see the second defect of optical image, which is Rayleigh criteria. So according to Rayleigh criteria for diffraction, limit to resolution state that two images are just resolvable when the center of diffraction pattern of one is directly over the first minimum of diffraction pattern of another, right? So this is very much important. Rayleigh criteria help us to determine how we can relate diffraction, right? So according to it, diffraction limit to resolution state that two images are resolvable when the center of diffraction pattern of one is directly over the first minimum of diffraction pattern of other. The first minimum is at an angle theta, which is equals to 1.22 lambda by d, right? So what is lambda? Lambda is wavelength of light, d is diameter of aperture, lens, mirror, etc., whatever we are using here for diffraction phenomena, with which the two objects are observed. In this expression, theta has units which is of radian. So here you can see these are the two minimums which we need to go for, right? And these are object 1 and object 2. When they send or when they supply light, so they will have two different intensities as they are at two different places. So here you can see both the graph A and B. Graph A is a graph of intensity of diffraction pattern for a circular aperture. Similar to single slit, the central maximum is wider and brighter than both the sides. So here you can see this is more intensified than this side or this side, right? And in second figure here you can see 2 point objects which will produce overlapping diffraction pattern. You can see source 1, source 2, there are two bulbs, one is this one and second is this one. They will produce a light and that light will have an overlapping pattern. Third defect is fringe width defect or fringe width and dispersion. So what do we understand by fringe width and dispersion? Fringe width of the principal maxima is sharpened as n is increased, right? So we can increase the fringe width if our n is increased. So it can be determined using formula del theta equals to lambda by n d cos theta. This gives angular interval from the peak of first minimum for the principal maximum that occur at theta, which is corresponding to order n. We must remember it is corresponding to order n. For the central maximum where theta is equals to 0, we can substitute cos 0 is 1. So it is del theta equals to lambda by n d. Dispersion: when a composite pencil of light is incident on a grating, different colors are separated from each other forming dispersion spectrum. This separation of colors or wavelength is known as dispersion. The dispersion d of the grating is then defined as angular separation per unit interval of wavelength, and it is given by the phenomena of dispersion d is given by delta theta upon delta lambda, right? So this is all about defects of optical images. And so this is all about defects of optical images. We have one more defect, which is resolving power of a grating. The resolving power of a grating is basically defined as power of separating two very closely situated spectral lines. Again, power of separating two very closely situated spectral lines is termed as resolving power of grating. It is denoted by Rp, which is equals to lambda by delta lambda, and it is equals to capital N into small n. The resolving power generally increases with order number. It depends on number of line, that is capital N, but it is independent of their separation D, right? So these are four defects which we must remember and understand for having better understanding of diffraction.